For years, the universe was said to contain around 100 or 200 billion galaxies. James Webb is making that number look incomplete, as it pushes deeper into the early infrared universe. It keeps revealing that far more galaxies may have been hidden from view all along. The real number could be closer to 2 trillion. And if that is true, then the early universe was far more crowded and active than we ever realized. When people said the universe has about 100 billion or 200 billion galaxies, that was not a final count. It was not astronomers saying they finished the job and closed the case. It was a lower floor based on what telescopes could actually detect well enough to count. That sounds like a small correction, but it changes the whole story. Because once you understand that, the real headline is not that the number got updated. The real headline is that most of the galaxies may have been missing from view the entire time. So why did the smaller number spread everywhere if it was not the full picture? Because it was simple, clean, and easy to repeat. Public science communication often turns a messy estimate into one memorable line. 100 billion galaxies is easy to say. At least trillions, if you include the faint galaxies below direct detection limits, is much closer to the real science, but it is harder to explain fast. That is how the smaller number became famous. Not because it was a lie, and not because astronomers were careless, but because the public version was simplified until all the uncertainty disappeared. And that is where the story gets much bigger. In 2016, a major analysis pushed the estimate to around 2 trillion galaxies in the observable universe. That number did not come from somebody suddenly spotting trillions of new galaxies one by one. It came from asking a harder question. If telescopes only see the brighter galaxies clearly, then how many smaller and fainter galaxies are being missed? Once astronomers started correcting for that hidden population, the total jumped massively. So the important change was not just the size of the estimate. The important change was the reason behind it. The universe did not suddenly create more galaxies. We started taking the invisible ones seriously. That is the real shock. Most galaxies may not have been left out by accident in some minor way. Most galaxies may have been left out because they were too dim for older telescopes to pick up directly. That means the cosmic map people got used to was built from the bright part of the population, not the full population. In other words, we were looking at the easiest galaxies to see and treating them like they represented everything. They did not. They represented the visible fraction. And in a universe this large, that difference is enormous. Now stop on that for a second. The universe is about 13.8 billion years old. Our Milky Way is just one galaxy among billions. Even NASA's public explainers use language like that because the scale is already extreme before you add any new twist. So when you hear that the old count may have been missing huge numbers of galaxies, this is not a tiny technical revision. In a cosmos this large, even a modest underestimate turns into a massive error in total numbers. If you miss a small percentage of a giant population, you already miss an absurd amount. If you miss the majority, the scale of that mistake becomes hard to even think about. So the issue was never just the number itself. The issue was what the number actually meant. Older galaxy counts were based on detection limits. Telescopes can only count what they can see clearly enough. That means every count comes with a built-in boundary. Bright galaxies above the threshold show up. Faint galaxies below the threshold mostly do not. The farther out you look, the worse that problem gets. The earlier universe is not just far away, its light is weaker, stretched, and much harder to capture. So the count problem was always tied to the limits of the instruments. It was never just about how many galaxies exist. It was also about how many our tools were physically capable of revealing. And that is why the jump to 2 trillion matters so much. Not because astronomers wanted a more dramatic headline, but because the analysis argued that the missing population was not small. It argued that the missing population may be the majority. That flips the entire tone of the story. It means the visible universe we were used to talking about may have been only the bright surface layer of something much denser underneath. It means the earlier picture was not false, but incomplete in a much deeper way than most people realized. Then there is another uncomfortable point. People often hear a revised estimate and assume science was confused before and then finally fixed itself. That is too simple. The older number was not wrong in the careless sense. It was limited by what could be measured directly at the time. That is normal in frontier science. First you detect what is easiest to detect, then you build better tools, then you test whether the hidden population you inferred is really there. That is how the field moves forward. So this is not a story about failure. It is a story about how a rough lower flaw got repeated so often that people forgot it was only a flaw. And that is where the tension starts building. Because if astronomers were already saying in 2016 that the observable universe could contain around 2 trillion galaxies, and if that estimate depended on huge numbers of faint galaxies hiding below older detection limits, then the next question becomes serious very fast. Can a new telescope actually start finding the kinds of galaxies that analysis said had to be there? Can it move the discussion from inference toward observation? Can it start showing that the early universe was not just populated but crowded? That is why James Webb matters in this story. Not because it magically created a bigger number, and not because it instantly counted everything, but because it is finally starting to reach into the part of the universe older telescopes struggled to see. That changes the stakes. The story stops being, astronomers came up with a larger estimate, and becomes something much stronger. The early universe may have been physically more packed, more active, and more mature than expected. And if that is true, then this is no longer just a correction to a popular fact. It is a shift in how you understand cosmic history. The central tension is simple now. If the universe already looked overcrowded on paper in 2016, then Webb matters because it is starting to detect the kinds of galaxies that paper said should exist. And once that starts happening, the argument changes. This is no longer just about whether the total is 200 billion or 2 trillion. It becomes a question of how much of the real universe was hidden from us, how early galaxies showed up in serious numbers, and how quickly the cosmos became crowded with structure. If the older number was only a flaw, then the next problem gets harder immediately. Why could Hubble, the telescope that changed astronomy, still not finish the count? Hubble changed astronomy, but it was never going to finish this count. That is the part people miss. Hubble gave us some of the deepest images ever taken. It showed that the universe was filled with galaxies almost everywhere it looked. It pushed farther than any telescope before it and completely changed how we see the cosmos. But even with all of that, Hubble was not built to settle the biggest part of this problem. The earliest galaxies are so far away that their light does not reach us in the same form it started in. By the time that light arrives, a lot of it has been stretched out of visible light and moved into infrared. So Hubble was revolutionary, but it was still hitting a wall. It could reveal an enormous amount, but not the era that matters most if you are trying to understand how many galaxies were there near the beginning. So what exactly was that wall? It was not distance by itself, it was what distance does to light. The farther back you go, the more the expansion of the universe stretches starlight into longer wavelengths. Light that started out in ultraviolet or visible bands gets pulled redder and redder during its journey. By the time you're trying to detect galaxies from the first few 100 million years after the Big Bang, visible light astronomy is no longer enough. You are looking in the wrong part of the spectrum. It is like receiving a signal that has been shifted so far from its original form that your instrument is no longer tuned to catch it properly. That is why the earliest universe was so hard to access. It was not just faint, it was shifted out of the range where Hubble was strongest. And that is where the count problem becomes much more serious. If your telescope is best at visible light, then as you look farther and farther back, more of the galaxies you care about start slipping out of view. Not because they are not there, and not because the math was wrong, but because the universe itself is moving their light into a different regime. So when astronomers tried to use older observations to estimate the total galaxy population, they already knew they were missing part of the picture. The farther back they wanted to look, the more severe that problem became. That means the oldest and faintest galaxies were exactly the ones most likely to escape direct detection. And those are also the galaxies that matter most if you are trying to understand whether the real census is far above the popular number. That is why Webb is not just Hubble, but better. Webb is a different class of machine. It was designed around this exact problem. Its main mirror is 6.5 meters across, about 21.6 feet, and that matters for a very simple reason. A bigger mirror gathers more light. More light means better sensitivity to very faint objects, but size is only part of it. Webb was also optimized for infrared wavelengths, which is exactly where the earliest galaxies have been shifted by cosmic expansion. So this is not just a newer telescope with a sharper view. It is a telescope built to observe a part of reality that older instruments could not fully reach. Hubble could hint at the first galaxies. Webb can go after them directly. That difference changes the mood of the whole story. With Hubble, astronomers could see deep into space and build extraordinary maps of the bright universe. With Webb, they can push into the redshifted universe where the first galaxies actually live. That is why people talk about Webb as if it opened a new window, because that is basically what happened. The light was always coming. The problem was that we did not have the right tool to catch enough of it. Once you move into deep infrared with much stronger light-gathering power, objects that were barely suggested before start becoming real targets. Then there is another point people often miss. Even the most famous deep images are tiny, really tiny. When you see one of these deep fields filled with galaxies, it feels like astronomers scanned a huge part of the sky and counted everything in it. That is not what happened. Webb's first deep field covered an area of sky about the size of a grain of sand held at arm's length. That is a tiny patch, almost nothing compared to the whole sky. And even that tiny sliver was crowded with thousands of galaxies. That should completely reset your intuition. The universe does not have to look empty across the sky for the total number to be huge. Astronomers take very deep samples in very small regions, measure how crowded those regions are, and then use that information to infer the much larger population. So galaxy counting is not done by sweeping the whole sky, object by object, until you reach some final total. That would be impossible. The real method is more like taking core samples from an ocean you cannot drain. You go incredibly deep in very small areas. You measure how many galaxies appear at different distances and brightness levels. You correct for what is too faint to see directly. Then you scale that up across cosmic volume. That is why the quality of the telescope matters so much. A deeper infrared telescope does not just add a few extra dots, it changes the density of the sample. And once the sample gets denser, the inferred total for the whole observable universe can change by a massive amount. This is also why the old account was never careless. It was incomplete in the way every frontier measurement is incomplete. Hubble showed us the bright structure of the universe with extraordinary power. It revealed the broad outline, the major populations, the visible framework. But it could not fully reach the earliest and faintest galaxies that may make up a huge fraction of the total population. That is not failure. That is exactly what happens at the edge of measurement. First you detect the part you can reach, then you build the instrument that can go farther. And that is the clean takeaway from this section. Hubble showed the bright skeleton of the universe. Webb was built to go after the missing flesh, and once you realise that, the next question gets a lot more intense. If Webb can finally reach into the faint infrared universe where the hidden galaxies were supposed to be, then where did the 2 trillion figure actually come from in the first place? The 2 trillion number was not a wild guess, and it was not somebody trying to make the universe sound bigger for a headline. It came from a real attempt to solve a specific problem. Astronomers already knew that direct images only show part of the galaxy population, especially when you go to very faint objects and very early cosmic time. So instead of pretending the visible sample was the whole answer, they asked a harder question. In different periods of cosmic history, how many galaxies seem to exist in a given amount of space, and how does that total build up when you add those periods together across the observable universe? That is how the estimate was built. Not by counting every galaxy one by one, but by taking observed galaxy number densities at different redshifts, combining them with cosmic volume, and pushing the calculation down to low stellar masses, where lots of small galaxies should exist. One route in the analysis gave around 2.8 trillion, another gave around 1.2 trillion. The authors then averaged those approaches and landed on about 2 trillion galaxies as a lower limit. That sounds technical, but the basic idea is simple. You're not trying to tag every galaxy individually like you are checking names off a list. You are measuring density. You are asking how crowded the universe looks in different slices of time and different ranges of galaxy mass, and then scaling that up using the geometry of the observable universe. It is less like counting every tree on a planet one by one, and more like measuring how dense different forests are, checking how much land they cover, and then building the total from that. The physics matters because the universe changes over time. Galaxy populations are not the same at every distance and every epoch. So astronomers break cosmic history into slices, look at how many galaxies appear in each one, and then add those slices together. That is why the number sounds huge. It is not one direct snapshot. It is a population estimate built from many layers, and that is exactly why the phrase lower limit matters so much. The paper did not say this is the final number and the case is closed. It did not pretend to give a neat total with no uncertainty. It was explicit that the result depended on assumptions like mass limits and redshift limits. In other words, the answer depends on how far down into small galaxies you choose to go, and how far across cosmic history you think the estimate can be trusted under the available data. So when the paper says about 2 trillion, that is not a polished final census. It is already a cautious result. It is saying that under those assumptions, the observable universe contains at least that many galaxies, and that is what makes the number hit harder. Even the shocking version was conservative. That leads to the most important part of the whole argument. The paper said the visible galaxies in the images were not the full population. A huge part of the total was likely hiding below direct detection thresholds. In particular, the authors argued that galaxies fainter than about magnitude 29 made up a major missing population. In plain language, these are extremely dim systems. They are small, faint, and hard to pull out of direct imaging. Some barely register at all, some do not register in any useful way. But even if each one is faint, they can still dominate the total count because there may be so many of them. That is the key. The universe does not need each hidden galaxy to be impressive on its own. It just needs there to be enormous numbers of these dim systems spread through cosmic history. And once you understand that, the jump from the old popular number to the 2 trillion estimate stops looking random. It came from taking the faint end seriously. If you only count the galaxies bright enough to show up clearly, your total stays much smaller. If you model the vast population of tiny, dim galaxies that should exist below that line, the total rises very fast. That is why the increase was so large. It was not because astronomers found one extra class of objects and added a little correction. It was because the unseen population at the faint end may be huge. That is why the inferred total jumped by nearly an order of magnitude compared with the kind of number people were used to hearing. This also explains why the 2 trillion claim was so important before Webb even launched. It was making a prediction about the hidden universe. It was saying that the missing majority likely lives in the faint universe, in the part of cosmic structure older telescopes could not directly map very well. So the question after that paper was simple but brutal. If most galaxies are hiding below previous detection limits, can a new telescope finally start reaching them? Can it at least begin to detect the front edge of that hidden population? Can it move the discussion from inference toward evidence? That is where the story turns directly toward James Webb. Webb does not need to find all 2 trillion galaxies itself. That is not the point. The point is whether deeper infrared observations keep uncovering more faint, early and previously hidden systems in exactly the direction this estimate predicted. If the answer keeps coming back yes, then the logic behind the larger census gets stronger, because the 2 trillion number was never about magic. It was about a missing population that should be there if the universe is as crowded as the model suggested. So this section really lands on one idea. The famous larger number came from measured galaxy densities, cosmic volume, and an attempt to include small faint galaxies that older direct counts were missing. It was not a random upgrade. It was a structured estimate, and even then it was framed as a lower limit, which means the shocking number was already the cautious version. And once astronomers said the missing majority probably lived in the faint universe, the next step became unavoidable. Could a telescope built for deep infrared finally start finding them? Webb matters because it is built for the exact part of the universe that older telescopes struggle to reach. Its strength is not just that it is newer. Its strength is that it's optimized for infrared light. And that is where the earliest galaxies are now visible to us. Those galaxies are so far away that cosmic expansion has stretched their light out of the visible range and into infrared wavelengths. That changes everything. Hubble could give hints. Hubble could show that something was out there. But Webb is designed to work directly in the part of the spectrum where those first galaxies actually show up. So this is not a small upgrade. It is access to a different observational regime. That point is easy to underestimate, so keep it simple. The first galaxies are not just extremely distant. Their light has been changed during the trip. What left those galaxies as shorter wavelengths arrives here as longer wavelengths. If your telescope is not built to work deeply in infrared, then a lot of that early universe stays out of reach. That is why Webb is so important to the galaxy count story. If the missing population is faint, ancient, and heavily redshifted, then you need a telescope that can operate exactly where that light ends up. That is what Webb was made to do. Then there is the mirror, and this is not just a spec sheet detail. Webb's main mirror is 6.5 meters across, about 21.6 feet. That means it gathers much more light than Hubble, and in astronomy that is everything when you're hunting faint objects. A bigger mirror gives you stronger sensitivity. It lets you pick up weaker signals. It lets you study galaxies that would otherwise stay below the threshold. And when you combine that with infrared optimization, you get the real reason Webb is so powerful. It is not just seeing farther in a simple sense, it is pulling in enough redshifted light to make the faint early universe measurable instead of almost invisible. That is where Webb stops sounding like just another observatory and starts sounding like the tool astronomers were waiting for. Because when you're trying to study galaxies from the first few 100 million years of cosmic history, you are not looking for bright, easy targets. You're looking for weak signals from objects that are small, distant, and shifted into infrared. That requires sensitivity, not just resolution. It requires a machine that can collect a lot of light and do it in the right wavelength range. Webb has both. That is why it can push into places older instruments could only approach indirectly. And Webb does not just take pretty deep images. This is another major difference. In surveys like JADES, Webb used NIRCam to find faint galaxy candidates, and then used NIR spec to measure their redshifts and study the gas and stars inside them. That combination is a big part of why Webb is so dangerous for old assumptions. First, it detects extremely faint targets in deep imaging. Then it follows up with spectroscopy. That second step matters because an image can suggest a galaxy is very distant, but spectroscopy can confirm it. Spectroscopy turns a candidate into a measurement. It lets astronomers pin down how far away the object really is and start learning what is physically happening inside it. That is why Webb is not just better at seeing dim smudges, it is better at proving what those smudges are. And that matters a lot in this story because galaxy counts become much stronger when distances are nailed down instead of estimated loosely. If you want to argue that the early universe was crowded, you need more than suggestive dots in a deep field. You need confirmation, you need redshifts, you need real data on the objects themselves. Webb's strength is that it can find these galaxies and then force them through spectroscopy until distance becomes a measurement instead of a guess. Its wavelength coverage is also a huge part of the story. In JADES imaging, Webb observed in multiple infrared bands from about 0.9 to 4.44 microns. That already pushes well beyond normal visible light work and into the region where many early galaxies become accessible. Then MIRI goes even farther into the mid-infrared, with a range NASA describes as 5 to 28 microns. That range matters because it gives Webb access to light that visible light telescopes simply cannot study the same way. The scientific language is microns, and that is the right way to say it. The simple version is that Webb is built to catch light that older visible light astronomy lets slip past. And when you put all of that together, the galaxy count argument becomes much sharper. The case for trillions of galaxies depends heavily on faint populations, especially small and distant systems that older telescopes struggle to detect directly. Webb does not need to find every one of them. That would be impossible. It just needs to show that when you push deeper into infrared space, more galaxies keep appearing. Earlier ones, fainter ones, stranger ones. The moment that keeps happening, the logic behind the larger sensors gets stronger. That is exactly what makes Webb the perfect galaxy hunting weapon. It works in the right wavelengths. It gathers enough light to reach extremely faint targets. It combines deep imaging with spectroscopy so distance can be confirmed. And it keeps pushing the frontier toward objects that were once expected to stay hidden. So the important question is no longer whether Webb can find a few rare early galaxies. The important question is what happens when it stares into tiny patches of sky and finds that they are already packed. The early universe already looks crowded, and the evidence is not subtle anymore. In one JADES image of the Goods South region, NASA says more than 45,000 galaxies are visible. Stop on that number. That is not the whole sky, that is not even a large part of the sky. That is one deeply studied patch, one region, one field, and it already contains tens of thousands of galaxies. That should immediately change how you picture the cosmos. The universe is not lightly sprinkled with galaxies here and there. When you look deeply enough, it is packed. And that matters because this is exactly how the galaxy count argument gets real. A lot of people hear a number like 2 trillion and think it must be abstract, or too dependent on models to feel solid. But when Webb stares into one carefully chosen region and the image fills with galaxies at different distances and different ages, the argument becomes much easier to understand. The point is not that astronomers guessed a big number and hoped it would hold up. The point is that every time the telescope goes deep enough, the sky gets crowded fast. Not a little crowded, extremely crowded. Then CEERS widens the case beyond one famous image. This is important because you do not want the whole story hanging on a single dramatic field. The CEERS program was built to target the early universe directly. It aimed to discover about 20 to 80 galaxies at redshifts around 9 to 13. And at the same time it planned to obtain deep spectra for more than 400 galaxies at redshift above 3. That changes the tone completely. This is not one weird record-breaking object that happened to show up in the right place. This is Webb building real samples. Large enough samples to start testing how common early galaxies actually are, how bright they are, and how quickly structure appeared. That is a major shift from older discussions. Before Webb, a lot of the earliest galaxy conversation was built around hints, sparse candidates and small numbers. Now the field is moving towards populations. That does not mean every mystery is solved. It means the telescope is no longer just catching isolated surprises. It is collecting enough objects to show patterns. And once you start seeing patterns, the argument gets much stronger. Because one strange galaxy can always be dismissed as an outlier. A growing sample cannot be dismissed that easily. Then go back to Webb's first deep field because it still hits hard. SMACS 0723 was described by NASA as teeming with thousands of galaxies, including the faintest infrared objects ever observed at that time. And Webb reached that depth in about 12.5 hours. That is one of the most important reality checks in this entire story. Hubble's deepest infrared fields took weeks. Webb pushed past them in roughly half a day. That tells you the universe did not suddenly become more crowded when Webb launched. The crowd was already there. Webb simply became powerful enough to reveal it. That is the line that really matters. The universe did not change. Our access changed. And once access changed, the old idea of a relatively sparse early cosmos started looking much weaker. Because when a telescope can go deeper, faster, and in the right wavelengths, it keeps uncovering more galaxies in the same tiny patches of sky. That is exactly what you would expect if the hidden population is real. The deeper you go, the more the missing universe starts leaking into view. This is why density matters more than headlines. The real story is not just that Webb found a distant galaxy, or broke a record, or produced a sharper image. The real story is that every time Webb looks hard into a tiny patch, it finds galaxies stacked through cosmic time. Some are closer foreground systems, some are much farther back. Some lived within the first billion years of the universe. They are layered through the line of sight like a deep history of structure formation. And if that level of crowding is common across the sky, then the full observable universe fills up very fast. That is how the count problem should be understood. It is a density problem first. If a very small field already contains thousands or tens of thousands of galaxies, then scaling up to the whole observable universe is naturally going to produce enormous totals. The question is not whether that sounds too big emotionally. The question is whether the observed density in these deep fields is real and representative. And so far, Webb keeps pushing in the same direction. Deeper observations do not clean the field up. They make it denser. That should also change how you think about hidden structure. The older window into cosmic dawn was narrower, shallower, and much more dependent on visible light. So of course it was going to miss part of the population. The issue now is how much it missed. And that is where the tension rises again. We are no longer arguing over whether the universe contains many galaxies. That is already finished. We are now arguing over how many layers of structure were missed, because the old window could not reach far enough into the faint infrared universe. And once you accept that the early universe is already looking packed in these tiny deep samples, the next question becomes much harder to ignore. If Webb keeps finding galaxies in huge numbers, just how far back is that crowding starting? Because the next step in this story is where the timeline itself starts getting squeezed. The distance record started turning this from a galaxy count story into a timeline problem. Once Webb began confirming galaxies at extreme redshifts, the issue was no longer just that the universe had a lot of galaxies. The issue became that some of them were showing up much earlier than many people expected. The first hard blow was JADES-GS-Z 14-0. Webb spectroscopically confirmed it at a redshift of 14.32, placing it at less than 300 million years after the Big Bang. Nature described that result as evidence that luminous galaxies were already in place that early and were more common than expected before JWST. That is the moment where the story changes from "there may be more galaxies" to "some galaxies were arriving much too early." Then the case got sharper. NASA reported JADES GS-13-1 at a redshift of 13.05, seen just 330 million years after the Big Bang, and it showed unexpectedly strong Lyman alpha emission. That matters because this is not just a distant object showing up as a faint point of light. This is spectral information coming from a galaxy, in an era that should still have been filled with neutral hydrogen fog that blocks that signal. So Webb was not only finding galaxies very early, it was getting detailed physical information from them in a period of cosmic history that was supposed to be much harder to read clearly. Then the frontier moved again. In January 2026, NASA reported MOM-Z14 within a redshift of 14.44, corresponding to about 280 million years after the Big Bang. NASA also said its light has been travelling for roughly 13.5 billion years through expanding space. That pushes the record line even deeper into the universe's infancy. Put simply, the record frontier is now pressing into roughly the first 2% of cosmic history. That is an extreme place to be finding a galaxy bright enough to confirm, and this is why redshift records matter so much. Every time the record moves, the timeline for galaxy formation gets tighter. Gas has to collapse, it has to cool, stars have to turn on, heavy elements have to start appearing. Some systems then have to become bright enough for a telescope to detect from across expanding space. If galaxies this luminous already exist by about 280 to 330 million years after the Big Bang, then those processes were happening very fast. The universe was building visible structure on a shorter schedule than many pre-Webb expectations allowed. So the real shock is not just that Webb found the farthest galaxy yet, The real shock is that every time the record moves, it drags galaxy formation deeper into the universe's earliest phase and leaves less time for theory to breathe. And once that starts happening again and again, the next question gets even hotter. If these galaxies are showing up this early, why are some of them also brighter than they were supposed to be? The problem changed again when Webb stopped just finding early galaxies and started finding bright early galaxies. That is a much bigger issue. The spectroscopic confirmation of galaxies at redshift 14.32 and 13.90 showed that luminous galaxies already existed about 300 million years after the Big Bang, and that they were more common than astronomers expected before Webb launched. Older models generally lean toward the earliest galaxies being rarer, dimmer, and much harder to detect in numbers. Webb pushed straight into that assumption and started weakening it. Then MOM-Z14 raised the pressure even more. NASA described it as part of a growing population of surprisingly bright early galaxies, and the Webb release says the research team argues that objects like this may be about 100 times more common than pre-launch theoretical studies predicted. That is the kind of claim people would normally treat with suspicion, except here it is coming out of a Webb science result tied to direct observation. So this is no longer just one bright outlier making trouble. It is starting to look like a pattern. And brightness this early is a real problem for older expectations. A galaxy that bright only a few 100 million years after the Big Bang suggests that something happened fast. Gas had to collect fast. Stars had to form fast. Enough light had to build up fast. In some cases, that could mean very intense star formation. In other cases, it could point to compact stellar populations or other mechanisms that make young galaxies visible sooner than expected. However the details work out, the message is the same. The early universe was supposed to still be in a rougher construction phase, but Webb keeps finding places where the lights are already on. That inference follows from the timing and luminosity of the confirmed objects. That loops straight back to the big galaxy count argument. Bright galaxies do not automatically get you to 2 trillion by themselves, but they do make the larger logic harder to ignore. If the bright end of the early galaxy population is already more abundant than expected, then the unseen faint end becomes even more important. You do not prove the hidden majority just by finding luminous record holders, but if the front row is already overcrowded, it becomes much harder to believe the back row is empty. Webb keeps pushing the evidence in the opposite direction. So now the problem is not, can Webb find early galaxies? That part is over. The problem is, why are there so many bright ones so soon in a universe that was barely out of its opening stage? And once that question lands, the next tension gets even stronger. If these galaxies were already bright that early, could they also have started changing the state of the universe around them earlier than expected? The early universe was not just dark, it was blocked. For a long stretch of cosmic history, space was filled with neutral hydrogen gas that stopped a lot of ultraviolet light from travelling freely. That period is called reionization. NASA describes it like a fog that had to be cleared before light could move across intergalactic space without being shut down. That means the first galaxies were not just sitting there waiting to be counted, they were forming inside a universe that was still hard to see through. So this is not only a galaxy census problem, it is also a transparency problem. The universe itself had to change state before light from the earliest structures could move freely across space. That is why JADES GS-Z13-1 hits so hard. NASA says this galaxy is seen just 330 million years after the Big Bang, and it shows strong Lyman alpha emission. That signal should have been very difficult to detect if neutral hydrogen were still filling everything around it in the same thick way astronomers expected for such an early time. So the result points to something important. At least some regions of the universe may already have been unusually clear, or this galaxy and sources around it were already carving out transparent zones much earlier than expected. In other words, Webb is not just finding a distant galaxy here, it is catching evidence that parts of the early universe may already have started opening up. NASA's description of the geometry makes the scale of that result much easier to feel. The transparent region around the galaxy was described as huge compared with the galaxy itself, like a pea suspended inside a hot air balloon. That comparison matters because it shows how extreme this process is. You have a tiny early galaxy, but the zone around it that has become ionized is much larger than the object doing the work. So the picture is not small and quiet. It is a violent local change in the state of the universe. A compact source turns on, intense radiation escapes, and a giant bubble of clearer space starts opening around it. And this loops directly back to the galaxy count story. If reionization was driven in large part by many small galaxies, then the faint population is not some side detail in the background. It becomes central to cosmic history. Suddenly those hidden dwarf systems matter for more than just increasing the total number. They may help explain how the universe itself became transparent. That means missing faint galaxies is not only a bookkeeping problem, it can mean missing the main population that helped reshape intergalactic space during cosmic dawn. That is why the hidden population matters so much more now than it did in the simpler old version of the story. So the first galaxies were not passive points of light sitting in the dark, they were changing their surroundings. They were building the conditions that let later light travel farther. And if small galaxies did a large share of that work, then leaving them out of the census means leaving out the engine room of cosmic dawn. Which brings the tension up again, because if the hidden majority may have helped clear the fog, then the next question gets even worse for the old picture. What if most of the universe's galaxies were always there, just too small and too faint for us to see? The core claim has not changed. It has only become harder to ignore. The 2016 analysis argued that most galaxies in the observable universe were too faint for the technology of that time to see directly. Not a small extra population, not a minor correction at the edges, the majority. That is the foundation under this entire story. The famous smaller numbers came from the part of the galaxy population telescopes could detect well enough to count. The much larger estimate came from asking what happens when you include the enormous population of faint systems that should exist below that line. A Science Daily summary of the 2016 work says the conclusion was that about 90% of galaxies in the observable universe were too faint and too far away to be seen with their present-day telescopes. That point matters because the total census is usually not controlled by the bright showpieces people remember. The spectacular record breakers get the headlines because they are easy to talk about. They are large, bright, distant, dramatic, and easy to turn into a single sentence. But total population counts do not work that way. In the 2016 estimate, astronomers integrated the galaxy population down to a stellar mass of about 10 to the 6th solar masses, and the count rose sharply because low-mass galaxies pile up fast. That is the real logic here. The universe does not need every galaxy to be giant to reach a huge total. It only needs huge numbers of small galaxies. So cosmic history may be dominated, in a counting sense, by the tiny systems that did not stand out enough to get noticed before. And once Webb started looking deeper, the pattern began to support that idea instead of weakening it. Webb's first deep field revealed thousands of galaxies in a patch of sky about the size of a grain of sand held at arm's length. Then JADES looked into the Good South region and found more than 45,000 visible galaxies in one deeply observed field. That is not a random fluke. That is what keeps happening when the telescope goes deep enough and observes in the wavelengths where these distant systems actually appear. Push deeper, go redder, and the universe keeps giving you more galaxies. The sky does not get cleaner, it gets denser. That matters because it changes the emotional center of the galaxy count story. The old version sounds like this. Astronomers had one number, then they revised it upward. The real version is much sharper. Astronomers suspected there was a huge faint population hidden below older detection limits, and now every time Webb pushes harder into the deep infrared universe, the crowding keeps increasing in the direction that suspicion predicted. Webb does not prove every inference all at once, but it keeps making the hidden population idea look more serious, not less serious. And the hidden population is not just more little dots. This is where the story gets more uncomfortable. Webb is already showing that early galaxies can carry real internal complexity. NASA's Webb updates describe early systems with signs of dust and more mature physical properties than people often picture when they think about the first galaxies. In parallel, Webb studies are finding compact objects in the early universe that may host actively growing black holes, including the class now called little red dots. NASA says a large sample of these objects shows that nearly all of them existed within the first 1.5 billion years after the Big Bang, and that a large fraction show signs of containing growing supermassive black holes. So the faint universe is not just hiding more galaxies, it may be hiding galaxies with structure, dust, intense star formation, compact cores and black hole activity. That changes the meaning of the missing majority. If you're only thinking in terms of count, then the hidden population sounds like a bookkeeping issue. You had too few dots on the page and better telescopes add more, but once those hidden systems start looking physically rich, the problem gets bigger. Now, the missing majority may have been doing important work. They may have been forming stars early. They may have been merging into larger galaxies. Some may have been feeding black holes. Some may have helped drive reionization. Some may already have had dust or compact internal structure. So the old blind spot may not have been hiding empty placeholders. It may have been hiding a huge amount of real cosmic activity, and that is exactly why deeper observing matters so much. Every time Webb goes after the faint universe, it is not just testing how many galaxies exist. It is testing how much of cosmic history was happening in systems older telescopes could not study properly. When the first deep field shows thousands of galaxies in a tiny sliver of sky, and JADES shows more than 45,000 galaxies in one deeply observed region, the message is not subtle. The visible bright population was never the whole universe. It was the easier layer. The deeper layer keeps opening up only when the telescope has enough infrared reach and enough sensitivity to get there. This is also why the 2016 result still matters in the Webb era. That paper did not just throw out a bigger number. It made a prediction about where the missing galaxies should be. At the faint end, in the low-mass population, below the direct reach of older instruments. Webb is not done testing that. It probably will not finish the job by itself, but the direction of travel matters. If deeper infrared observations keep producing more galaxies, and if some of those early galaxies already show complexity instead of being simple featureless smears, then the older inference about a hidden majority becomes more plausible, not less. And there is a harder possibility sitting underneath all of this. The scariest possibility is not just that the universe has more galaxies than people thought. The scariest possibility is that most of the universe's galaxies were always there, always part of the story, always shaping reionization, always merging and forming stars and feeding black holes, and we barely had access to them. Not because they were unimportant, but because they were too small, too faint, too redshifted, and too far away for the older window we were using. That is the real tension now. The hidden majority may not be empty background. It may be where a huge amount of early cosmic history actually happened. And once that lands, the next question gets even more dangerous. If the invisible majority may have been small, faint, and everywhere, then what were those early galaxies actually like? Were they just primitive blobs? Or were they already building real structure much earlier than they were supposed to? A lot of people still picture the first galaxies as rough clumps with no real structure. That picture is getting weaker. Webb is showing that the early universe was not just full of faint blobs. NASA's Galaxy Evolution Explainer says Webb's combination of sensitivity and resolution in infrared light is revealing cosmic dust in the early universe that had been previously undetectable, and it also says the observed shapes of early galaxies have been surprising. In other words, Webb is not just finding more early galaxies, it is showing that some of them already had features and internal differences that older observations could not study directly. One of the strongest examples is a JADES galaxy at redshift 7.430, seen when the universe was only about 700 million years old. A Nature astronomy paper reported that this object contains a compact central core and an extended disk-like component. The central core has a half-light radius of about 80 parsecs, which is roughly 260 light-years. The disk has a half-light radius of about 400 parsecs, around 1,300 light-years. That is not what people usually mean when they say primitive blob. That is internal structure. It is a galaxy where different components can actually be separated and studied. And the details make it even more important. The same paper says the core is extremely compact while the disk is larger and actively star-forming, with different stellar histories in the core, disk and clump components. The core is older and denser. The disk is where the most recent star formation is dominating. So this is not just a shape on an image. It is a system with internal organization. Different regions are doing different things. That means that by only 700 million years after the Big Bang, at least some galaxies were already developing architecture instead of just existing as loose, uniform patches of light. That matters because morphology this early changes how you think about galaxy assembly. If you see bulges, disks, compact central components, and colour differences across a young galaxy, then organisation is happening earlier than many people would assume. The early universe starts looking less like a sea filled with random fireworks and more like a stage where some systems are already settling into recognisable forms. NASA's explainer says some Webb researchers identified spiral structures earlier than expected, and it also notes that the observed shapes of early galaxies have been surprising enough to force new questions, so the shift is broader than one object. Webb is showing that early galaxies can already have form, not just existence. This is where the broader survey work matters. CEERS did not just go looking for distant galaxies in a general sense. Its project goals explicitly included quantifying the first bulge and disk structures at redshift above 3. That means astronomers were already aiming to test when recognizable internal structure began to appear. Webb was built to attack exactly this issue with deep imaging and spectroscopy across multiple modes. So the discovery of structured early galaxies is not some accidental bonus. It sits right inside one of the telescope's major science goals. Webb's first deep field also helps widen the case. NASA's Galaxy Evolution Explainer says the SMACS 0723 field is overflowing with detail, and that thousands of galaxies, including the faintest infrared objects ever observed at that time, appeared in Webb's view. The same NASA page also says Webb's infrared vision is revealing new details about galactic interactions and evolution in the early universe. So when you combine that with the structural results from CEERS and JADES, the pattern gets harder to dismiss. This is not one oddly mature galaxy that happened to show up. Webb is opening a regime where early galaxies can be examined with enough detail to reveal structure, dust, and internal variation across multiple programs. And once you accept that, the worldview shifts again. If structure appears this early, then the early universe stops looking like a rough draft. It starts looking like a phase of accelerated construction. Things are not only forming early, they are organising early. Dust is appearing, shapes are appearing, internal components are appearing. NASA's explainer says Webb is now providing real data to study the relationship between dust, star formation, and galaxy growth across cosmic history, and it says that before Webb we simply could not see some of this evidence for ourselves. That means the old simple story of the first galaxies as mostly shapeless beginnings is no longer enough. And that leads straight into the next escalation. If some early galaxies already had compact cores, disks, dust, and internal structure, then the early universe was not only building galaxies fast, it may also have been building central black holes fast. And once Webb starts finding signs of that, the whole story gets even more intense. The story gets more intense once black holes enter it. Webb is not only finding galaxies very early in cosmic history, it is also finding signs that some of those early galaxies already hosted actively growing black holes. That matters because black holes make the young universe look even less quiet, less simple and less delayed than the older picture suggested. If early galaxies were already feeding central black holes while the universe was still in its chaotic childhood, then galaxy growth was not just happening fast, it was happening in a more violent and energetic way too. That does not directly tell you how many galaxies existed, but it tells you the early universe was not some slow, empty waiting room before real structure started. It was already busy. A very clean example is CEERS 1019. NASA reported that this galaxy hosts the most distant active supermassive black hole identified at the time of that release. The black hole existed just over 570 million years after the Big Bang and has a mass of about 9 million suns. Those numbers matter because they make the point concrete. You're not dealing with vague language like very early or surprisingly old. You're dealing with a central black hole that had already grown to millions of solar masses in a galaxy that existed when the universe was still extremely young. NASA also emphasized that this black hole is far less massive than the billion solar mass monsters found in some other early universe studies, which makes it especially useful. It looks more like a system that could help astronomers understand ordinary black hole growth in young galaxies, not just the brightest rare extremes. That is what makes CEERS 1019 so effective in this story. It is not just another dramatic record. It shows that active black hole growth was already underway in a measurable, physically interpretable way. A black hole of about 9 million solar masses inside a galaxy, just over 570 million years after the Big Bang, tells you that the central engines of galaxies were turning on early. So the first galaxies were not only making stars, at least some of them were also building and feeding black holes. That immediately raises the intensity of early galaxy evolution. Once black holes are part of the picture, the young universe becomes more energetic, more compact, and more complicated than the simple version most people carry around. Then Webb found something even more unsettling: the little red dots. NASA says these objects showed up in Webb data less than 6 months after science operations began, and a large sample indicates that nearly all of them existed within the first 1.5 billion years of cosmic history. NASA also says a large fraction of them show signs of containing actively growing supermassive black holes. That is a very strong shift in tone. Early black hole growth stops looking like a rare extra detail added to a few unusual galaxies. It starts looking like something that may have been common in the early universe. And if it was common, then the early galaxy population was even more active than the old simple narrative allowed. This is one of the most important places where Webb changes the conversation. Before Webb, you could still imagine that active black holes in the very early universe were exceptional cases, but the little red dots make that much harder to maintain. NASA's release describes them as a newfound galaxy class, and it says the team's analysis supports the idea that much of their light comes from accreting black holes rather than stars alone. That means some of the strange, bright, compact sources Webb is seeing may not fit neatly into the older categories people expected. They are not just more examples of familiar galaxies. They may represent a phase of early growth that astronomers had not properly mapped before Webb started seeing them in large numbers. And the uncertainty here is not a weakness. It is part of the tension. The little red dots are useful precisely because astronomers are still arguing about what they are. NASA's wording makes clear that they may indicate early black hole growth, but the broader scientific discussion is still active because these objects do not fit comfortably into the pre-Webb picture. That is exactly the kind of result that matters most in a story like this. Webb is not just filling in missing details in an already stable map. It is discovering populations that force people to ask whether the old categories were even complete enough. When a telescope starts producing new kinds of objects that do not sit neatly inside older expectations, that is when the field gets uncomfortable in the most productive way. This matters for the galaxy count argument, even if it does not hand you a direct total. If many early galaxies were feeding central black holes, then early galaxy evolution was more intense and more observable in some wavelengths than simple toy models assumed. Active black holes can make galaxies brighter in specific regimes. They can change the energy budget. They can affect how gas moves, how stars form, and how astronomers interpret what they are seeing. So while a black hole discovery does not directly add galaxies to the census, it does tell you that the early universe was physically busier than the older neat version suggested. More activity means more complexity, And more complexity usually means the hidden population matters even more, not less. It also connects back to the larger pattern Webb keeps revealing. First, early galaxies were showing up earlier than expected. Then some of them turned out to be brighter than expected. Then signs of reionization started appearing in places that seemed too early. Now black hole growth is showing up early too. Each one of those results pushes against the same comfortable picture from a different angle. The timeline is tighter. The structures are brighter. The environment is changing sooner. The central engines are already turning on. None of that automatically proves the 2 trillion figure, but together it builds the same mood. The young universe was denser, more active, and more developed than the older simple narrative suggested. So the point of this section is not just that black holes appeared early. It is that early black holes make early galaxies look more mature, more energetic, and harder to fit into slow-building models. The galaxy count story gets hotter because once you add active black holes, the early universe stops looking like a sparse collection of dim starter systems. It starts looking like a crowded arena where galaxies were already forming stars, building structure, and in many cases powering central black holes at surprisingly early times. And once that happens, the next escalation is unavoidable. If galaxies were already growing black holes so early, were they also assembling into larger structures faster than expected too? Galaxies do not live alone, and that is where the story gets even more serious. Webb is not just finding isolated early galaxies, it is finding signs that larger structures were assembling fast too. That matters because galaxy counts are one thing, but galaxy environments are another. A single bright galaxy is already a challenge for the older picture. A whole gathering of galaxies bound up in a growing structure when the universe is still very young is a much bigger challenge. Once protoclusters and cluster-like environments start appearing early, the whole timeline of structure formation starts feeling compressed. The universe does not just look crowded in a numerical sense, it starts looking organized earlier than expected. A strong example is JADES-1. NASA reported this distant protocluster with a mass of about 20 trillion suns. It is located about 12.7 billion light-years from Earth, which means we are seeing it as it was roughly 1 billion years after the Big Bang. NASA said that finding a protocluster of this size at that epoch will force scientists to re-examine ideas about how galaxy clusters first appeared. That is exactly why this result matters so much. A mass like that at a time that early sounds like the kind of structure you would expect later in cosmic history, not while the universe is still in a much younger phase of development. And this is not just a vague pile of galaxies somebody wanted to label dramatically. NASA's report says JADES-1 shows 2 key signs of a real protocluster: a large number of galaxies held together by gravity, and a massive cloud of hot gas detected in X-rays. Chandra picked up that hot gas, while Webb identified at least 66 possible member galaxies. That is important because it pushes the result beyond a loose over-density on an image. It starts looking like a serious piece of early cosmic infrastructure. A region with many galaxies, hot gas, large mass, and a clear future as a full galaxy cluster is not a decorative detail. It is evidence that the larger cosmic web may have been assembling faster than many models were comfortable with. That connects to a bigger point people often miss. Galaxies are not sprinkled randomly through space. They trace a much larger pattern. NASA's glossary explains baryon acoustic oscillations as sound waves from the early universe whose imprint still shows up in the large-scale distribution of matter. Today, that imprint appears as a small excess in galaxy pairs separated by about 500 million light-years. In simple terms, the large-scale clustering of galaxies still carries memory from the early universe itself. So when astronomers study where galaxies gather, they are not just making a map of isolated objects, they are reading the scaffolding of cosmic structure. That is why early protoclusters raise the stakes so much. If the universe is already building dense environments early, then the story stops being only about a larger head count. When many galaxies show up early in shared environments, you also get mergers, gas stripping, black hole activity, feedback, starbursts. and the first stages of cluster growth. The crowded universe becomes dynamically different, not just numerically larger. More galaxies in early time means more interactions. More interactions mean faster reshaping of matter, energy, and structure. A denser early universe is not just one with more dots on the map. It is one where more things can happen sooner, and this fits the broader pattern Webb keeps pushing. First, the telescope started finding galaxies earlier than expected. Then it found some of them were brighter than expected. Then it found signs that reionization may have been advancing earlier in at least some regions. Then it showed evidence for early black hole growth. Now it is helping reveal that large structures may have been assembling quickly too. Each step tightens the same pressure point. The problem is no longer whether early galaxies existed. The problem is how quickly the universe went from hot plasma and faint fluctuations to a web of luminous systems, active black holes, and growing clusters. JADES-1 is powerful because it takes that pressure off the level of individual galaxies and puts it onto the level of environment and large-scale structure. This also changes how the galaxy count argument feels. A huge galaxy total is already hard to picture, but when those galaxies start showing up in connected environments, the count becomes more than a big abstract number. It becomes a sign that the universe was building communities of galaxies, not just isolated objects on a tighter schedule than expected. That is a deeper shift. It says the early cosmos may not have been a sparse field with a few lonely islands of light. It may have already been developing neighborhoods, traffic, and the first serious knots in the cosmic web. And once you start thinking in those terms, the hidden population matters even more, because faint galaxies are not only part of the total, they may also be part of the mass, pressure, and interactions that help larger structures grow. So the real stakes here are bigger than one dramatic protocluster. The question is no longer whether galaxies existed early. The question is how fast the universe went from smooth plasma afterglow to a connected web of luminous systems, black holes, and growing clusters. Webb keeps pushing the answer in the same direction, faster than expected. And once that becomes the pattern, the next question becomes unavoidable. If the universe built so much structure so early, how do astronomers even count something that big without pretending they can see every galaxy one by one? There is no cosmic clicker. Astronomers do not scan the sky and count galaxies one by one until they reach some final total. That is not how numbers like 2 trillion are built. The real method is deeper and much more disciplined. Astronomers combine very deep images, redshift measurements, number densities, and careful extrapolations below direct detection limits. That is how the Hubble-era work got from the galaxies it could actually see to an estimate near 2 trillion in the observable universe. The logic was never we found them all. The logic was we measured the visible population, modelled how galaxy populations change with time and mass, and then estimated how many faint systems must exist below the line where direct imaging runs out. That sounds abstract until you look at how small the samples really are. Webb's first deep field covered a patch of sky about the size of a grain of sand held at arm's length, yet NASA said it was already teeming with thousands of galaxies, including the faintest infrared objects ever observed at that time. Then JADES went deeper in another region and NASA reported that more than 45,000 galaxies were visible there. Those are not wide surveys of the whole sky. They are tiny keyholes. Astronomers look through those keyholes, measure how crowded they are, and use that crowding to infer the larger population across cosmic volume. That is why density matters so much more than raw image impact. A deep field is not just a pretty picture. It is a statistical sample of the universe at many distances and many times. If a tiny patch already contains thousands or tens of thousands of galaxies, then the larger total can become enormous very quickly once you scale by area, depth, and cosmic history. This is exactly why the bigger galaxy count estimates do not come out of nowhere. They come from measuring how crowded these samples are, and then asking what the full observable universe must look like if those densities are even roughly representative. But images alone are not enough. A galaxy can look extremely red and seem very distant in a picture, but colour by itself is not the same as proof. This is where spectroscopy matters. Spectroscopy breaks light into its wavelengths and lets astronomers measure how much that light has been stretched by cosmic expansion. That gives them a real redshift. JADES used NIOSPEC for that purpose, and NASA reported that JDS-GS-Z 13-1 was definitively confirmed at a redshift of 13.05. NASA also reported that MOM-Z14 was confirmed with NIR-SPEC at a redshift of 14.44. So the record-setting claims in this story are not based only on suggestive colours or loose photometric estimates. They are based on direct spectral confirmation. That point is more important than it sounds. When a distance record is based on spectroscopy, the claim becomes much harder to wave away. It means the telescope is not just spotting unusual red dots and hoping they are ancient galaxies. It is measuring their shifted light directly. That turns dramatic discoveries into anchored data. And once enough of those confirmations start piling up, the broader picture gets stronger too. The claim that the early universe was crowded, active and mature earlier than expected stops sounding like a mood and starts sounding like a result. There is also a force multiplier built into some of these observations, gravity itself. NASA's description of SMACS 0723 explains that the combined mass of the galaxy cluster acts as a gravitational lens, magnifying much more distant galaxies behind it. In simple terms, the cluster bends and amplifies the light from background objects, helping Webb see galaxies that would otherwise be even harder to detect. That means some of the faintest and most distant galaxies become visible not only because Webb is powerful, but because the universe provides a natural telescope in front of them. Gravity helps do the observing. That matters a lot for the census problem. If some of the faint background population only becomes visible when lensing boosts it, then it tells you immediately that the unseen universe is not empty. It tells you there are galaxies sitting below normal detection thresholds, waiting for either better instruments or natural magnification to bring them into view. So gravitational lensing is not some side trick. It is one more line of evidence that the faint universe is real and physically populated. And this is the key thing to understand about cosmology in general. Indirect does not mean weak. In a field this large, the biggest numbers are almost always inferred from constrained samples, not counted object by object. Nobody counts all the stars in a galaxy one at a time either. You measure a part, understand the physics, constrain the uncertainties, and build upward from there. The same logic applies here. Deep fields, redshifts, spectroscopy, lensing, and population modelling are the tools astronomers use to count something too large to count directly. That is not a flaw in the method. That is the method. So this section should land on one clear idea. The galaxy count is not a guess, and it is not a list. It is an inference built from tiny but extremely deep windows into the universe, strengthened by spectroscopy and sometimes helped by gravitational lensing. The brilliance of Webb is that it keeps moving those constraints in the same direction, toward a universe that is fuller, denser, and earlier than the older simplified story suggested. And once that becomes clear, the next question turns into the biggest one of all. If Webb is pressuring so many older expectations, does that mean cosmology itself is broken, or does it mean something narrower and more interesting is under pressure? JWST has not destroyed the Big Bang. That is the lazy version of the story, and it is wrong. NASA's own little red dot explainer includes the section title, "Contrary to Headlines, Cosmology Isn't Broken." That matters because it cuts through the fake apocalypse fast. Webb is creating pressure, but it is not erasing the basic framework of modern cosmology. The exciting part is not that everything was wrong. The exciting part is that the broad picture can stay intact while the details of how structure formed get a lot more intense and a lot more uncomfortable. So what is actually under pressure? Models of galaxy formation efficiency are under pressure. Models of dust production are under pressure. Models of how quickly stars formed in the first galaxies are under pressure. Models of how fast black holes could grow are under pressure. Those are the places where Webb keeps forcing revisions. But the underlying framework is still held up by much deeper evidence: the expanding universe, the cosmic microwave background, and the early universe pattern of light elements. Webb is stressing the timetable and the mechanisms of assembly, not the basic fact that the universe expanded from a hot early state and evolved over 13.8 billion years. The cosmic microwave background is one of the deepest parts of that foundation. NASA's glossary says it is the oldest light we can detect, coming from when the universe was about 380,000 years old. The same glossary explains that this relic radiation is the afterglow of the hot young universe. And NASA's Cosmic History Overview says its temperature fluctuations are the seeds that later grew into galaxies. That means the large-scale framework is not suddenly up for debate every time Webb finds a surprising galaxy. The framework already includes a universe that starts hot, expands, cools, and carries early density differences forward into later structure. The real fight is over how fast those seeds turned into luminous galaxies, black holes, and clusters. And honestly, that is the more interesting outcome anyway. Everything was wrong is a shallow headline. The broad rules were right, but the universe used them more efficiently than expected is much stronger. It means the foundations hold, but the construction schedule got shredded. The universe did not break its own rules. It seems to have built stars, dust, bright galaxies, active black holes, and growing environments earlier or faster than many models predicted. That is a more serious scientific problem than a fake total collapse story, because it forces real revisions where the details actually live. This is also why Webb's results feel so powerful without needing to become anti-science clickbait. The telescope keeps finding early galaxies, bright galaxies, structured galaxies, black hole activity, and even evidence of fast-growing larger environments. None of that says the age of the universe is suddenly wrong. None of that says cosmic expansion did not happen. What it says is that theorists may have underestimated how quickly matter could organize itself into luminous systems under the known rules. That is a major correction, but it is a correction inside cosmology, not a destruction of cosmology. The cosmic microwave background makes that distinction especially clear. NASA's glossary says the CMB is present everywhere in the sky, and dates from the universe at about 380,000 years old, when it was still a hot, dense plasma. Those fluctuations in the CMB are not random decoration. They are the earliest mapped density differences that later became stars, galaxies, and clusters. So when Webb finds a galaxy earlier than expected, it is not overturning that foundation. It is challenging the way people modelled the route from those early seeds to the later structures we now observe. The seeds are still there. The issue is how aggressively the universe grew them. That nuance should raise the tension, not lower it. If cosmology were actually broken at the foundation, the conversation would become vague and chaotic very fast. But that is not what is happening. What is happening is sharper. The framework is standing, which means the stress is being concentrated into specific physical processes: how efficiently gas cooled, how quickly stars ignited, how dust built up, how radiation escaped, how black holes formed and grew, and how galaxies assembled in the first few 100 million years. Those are measurable, modelable problems. That is where the real scientific fight is happening now, so the real stakes are better than the lazy headline version. The most exciting discoveries in cosmology are rarely the ones that erase the whole framework. They are the ones that leave the framework standing, while forcing you to rethink how the universe actually used it. Webb is doing exactly that. It is not tearing down the map. It is telling us that the route from the early universe to galaxies, black holes, and clusters may have been much faster and much more efficient than the comfortable models allowed. And once that lands, the final question becomes the biggest one left. If Webb is this deep but still narrow, what comes next if you want to move from these needle-like samples towards something closer to a real full census? Webb is deep, but it is not wide. That is the obvious limit, and it matters a lot. Webb can drill into the early universe with incredible sensitivity, but its field of view is still narrow compared with the size of the sky and the size of the census problem. NASA says Roman is the mission that will work with Webb by pairing Webb's narrower but deeper vision with a much wider survey view. That is the right way to think about the next phase of this story. Webb is giving us extremely deep samples. Roman is expected to tell us how representative those samples really are on much larger scales. So this story is not over. Right now, we are still looking at the ocean through a very precise straw. That matters because the galaxy count problem was never just about going deeper. It was also about knowing whether the crowded deep fields Webb sees are rare, typical, or only part of a more complicated pattern. A narrow field can reveal astonishing detail, but a wider field tells you how often those details appear across the sky. NASA's Roman and Webb explainer says Roman surveys will offer a broad view of cosmic ecosystems and pinpoint rare objects, while Webb can follow those up with its narrower but more powerful vision. That combination is exactly what you want if your goal is to move from impressive discoveries to a fuller census. Webb can identify what is possible. Roman can tell you how common it is. Roman is also expected to push one of the biggest open questions much harder: how common the earliest bright objects really were. NASA says Roman should help determine how common early quasars are and could find tens of thousands of them, compared with only a handful Webb may detect in its smaller fields. That is a huge difference in scale. A handful can change theory. Tens of thousands can measure a population. And once you can measure a population, you can start answering bigger questions with much more confidence. Were the earliest luminous systems unusual? Were they everywhere? Were current Webb fields catching something special, or were they showing us the normal universe at that time? Roman is built to widen that context. That is why the future of this story is not Webb versus Roman. It is Webb plus Roman. NASA explicitly frames them as complementary. Roman's wider surveys can identify rare targets and map environments over larger areas, while Webb can go deeper and study selected objects in much more detail. In practice, that means the next leap in this field will not come from one telescope trying to do everything. It will come from one telescope finding the big statistical picture and the other telescope drilling into the physics of the most important targets. If you want to move from the universe looks crowded in these deep fields to here is how crowded it really was across cosmic dawn, that is the combination you need. And Webb itself is nowhere near finished. JADES is the perfect example of that. The survey overview says JADES will ultimately cover over 100 square arc minutes from 0.7 to 5 microns, plus 10 square arc minutes at 7.7 microns, and produce thousands of galaxy spectra. That is already a major data set, and it means the early universe sample is still actively growing rather than settling down into some final stable catalogue. Every time that archive expands, it increases the number of galaxies with real measurements instead of just suggestive detections. That makes the whole picture stronger, and the archive has already been expanding in exactly that direction. The STSCI JADES archive notes that one of the later public releases added more than 4,000 additional spectra, with 2,375 sources that had measured redshifts. That is a serious increase in confirmed information, not just cosmetic growth. More spectra means more secure distances. More redshifts means stronger timelines. And stronger timelines mean better constraints on how quickly galaxies, dust, black holes, and larger structures were appearing. So the early universe sample is not stabilizing into a finished story. It is still opening up. This is important because the endgame is not just getting a bigger number to put in a documentary line. The real goal is to connect the count to the physics. How many faint galaxies actually existed? How much did they contribute to reionization? How quickly did they assemble into structured systems? How early did they start forming dust? How soon did some of them begin feeding black holes? How fast did they grow into denser environments and protoclusters? Those are not separate questions anymore. The count, the physics, and the timeline are tied together now. Every new galaxy Webb confirms is not just another mark on a chart. It is one more piece of evidence about how the early universe actually worked. That is also why the phrase full census has to be handled carefully. No telescope is going to literally count every galaxy in the observable universe one by one. The full census will always be an inference built from deeper and wider observations, better spectroscopy, stronger statistics, and better modelling of what lies below direct detection limits. But that does not make it weak. It makes it more realistic. What matters is whether the constraints keep moving in the same direction. So far they do. Deeper Webb observations keep revealing more faint and early systems. Wider future surveys are expected to show how common those systems really are. And the more those two approaches line up, the closer astronomy gets to a much more complete answer. So the final mystery is not just, is the number 200 billion or 2 trillion? That is the public version of the puzzle. The deeper version is this: how much of the real universe was hidden below older detection limits? And what was that hidden universe already doing? Was it driving reionization? Was it building structure faster than expected? Was it feeding black holes earlier than expected? Was it already crowded with small systems that older telescopes could barely hint at? The future of this field is about answering those questions together, not one at a time, and that brings the whole story back to the two numbers people remember. 200 billion was the universe as it looked through an older window. It was the brighter, easier, more visible version of the cosmos. 2 trillion is the universe implied when you take the hidden populations seriously and account for the galaxies that older technology could not directly reveal. Webb's deepest message so far is that the hidden universe was not empty, not quiet, and not late. It was already crowded. It was already luminous. It was already building galaxies, shaping the medium around them, feeding black holes, and assembling larger structure on a tighter schedule than many models expected. That is why this story matters. It is not just a big account. It is a denser, earlier, more active cosmic history coming into view. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.